Hello. I think it's 1 minute before the start, so we can start. The recording has already started, so it's okay. Well, we were the road so far. We got so far to the lecture 8, right? What we did in the previous lectures, we covered some ground concerning normal forms. We discussed the case when Nijenhuis operator is diagonal. We discussed in great detail the case when Nijenhuis operator is a single Jordan block with constant or probably non-constant eigenvalue. And we, using Thompson's theorem, we a little bit tried to understand the geometry of the nilpotent case. And we have seen that in nilpotent case, we have a really wild geometry, right? We've looked at the case of L squared equals 0, and we have seen that the normal forms they're in one-to-one correspondence with the congruence classes of distributions. And this is impossible to classify, so this geometry is wild. So when we say Nijenhuis geometry, that's what we will mean. We will mean some manifold equipped with a Nijenhuis operator, and we see that different Nijenhuis operators, they give different geometries, and these geometries, they do look, and they have sometimes they have completely different properties. We have seen, for example, that if we deal with a diagonal operator and the eigenvalues they're not constant, then the symmetry group is rather small. So I'm sorry. Okay. So now we arrive to understanding that throughout all these examples, they all I've brought them together in one single table. Throughout all the examples, what we assumed is that the algebraic structure of the Nijenhuis operator does not change from point to point. Again, as you recall, the operators, they have a rich linear algebra. They have Jordan normal forms. Those Jordan forms can change. Not so much with a metric, for example, or in case of symplectic geometry, you actually have a single normal form in regular points and points considered to be regular. So in this case, we understand that it was expected. It was expected because the object in a point is more complicated than, for example, quadratic forms. Then we will have a lot of different geometries that when you add to the mix differential geometry to the mix of linear algebra, you'll get some complicated things. And that's what we did. Okay, that's what I've just explained. But now the next step is to study singular points, because, well, it turns out that in applications and in most of the cases, the Nijenhuis operators appear in the singular points are crucial one. It is expected, right? If you want to study a vector field on a manifold, right, you study its singular points, because those points, they do carry information about vector field and about the topology of the manifold. Same thing, same logic can be applied here. If we want to study the Nijenhuis geometry in the whole, if we want to look at the manifolds, right, which can carry the Nijenhuis structure, then we will have to deal with the singularities. But before deal with singularities, we need to deal with regular points. And this is again, the definition of regular points we have arrived to so far by doing a lot of research, by proving theorems. We see that algebraically generic point is the point, such point that around in the small neighborhood of this point, the Jordan block structure does not change. You see, you cannot say that Jordan normal form doesn't change, because eigenvalues, they do change. This is important, but the structure does not change. What does it mean? It means that if you have eigenvalues, they keep their multiplicity, right? And if you have some Jordan structure corresponding to the particular eigenvalue, then in each point, the Jordan structure, number and sizes of Jordan blocks, they do not change. It's altogether, this information is sometimes called Stingray characteristic. It is a term from linear algebra. You will meet it in if you start reading articles on our geometry. Okay, so that's what we're gonna do. We have discussed that we have the following regular points. They're algebraically generic, and that is the points we're interested in. We have been interested in. And here is some, again, interesting geometries. The one I forgot is the complex geometry. We have seen that in case of complex eigenvalues, we have a natural complex structure that appears, and we see that Nijenhuis geometry becomes very entangled with a complex geometry because we have the functions become holomorphic. And so we proceed to the next level. We want to study singular points. It is expected, of course, that if you have a lot of regular geometries, then you will have a lot of, like a great number of singularities. It is true, they are very complicated, and you have a lot of problems that may appear because if you look at the definition, what are the singular points? The singular points are the points where which are not algebraically generic, right? So what you do have is when you get close to this point, the algebraic structure of the operator, it becomes perturbed, it transforms, and this transformation can be wild. You can like see, if you know linear algebra well, you know that, for example, in the neighborhood of a Jordan block, right? You can take a Jordan block and you can perturb it, and you can obtain by a single perturbation any Jordan structure you want, any Jordan structure. For any given epsilon, you take a small perturbation of the Jordan block just by putting the first column. We will use it later, but this is how these perturbations, they can be wild. So it's a natural thing is to limit ourselves to start with the simplest possible case. What is the simplest possible case? Well, the answer to this, it comes from the applications of the Nijenhuis geometry, and it turns out that very, very often in infinite dimensional integrable cases or infinite dimensional integrable cases or in case of projectively equivalent metrics, you deal with an operator with a specific property. The specific property is like this. We call it differentially non-degenerate, and this implies that in a given point, the coefficients of the characteristic polynomials, they are independent. It means that you can take them as a coordinates, right? They're independent functions. The differentials are independent. If they're independent at the point, they're independent in sufficiently small neighborhood, and this is your coordinate. This is the map, like this is the neighborhood where these coordinates apply, where they do exist. So, I'm sorry. We start with a simple example. It is always good to start with an example, and this example it's very important because it allows us to see the effects. Like, why do we start with an example? Because you can starting with a special case of dimension 2, you can just look at the specifics, and you will see later which of these effects they are like general, and which of these effects are not. Right, and this is the power of this very good example. I advertise it too much, I think, but it's a very good example. I like it. So imagine that we have an operator like this. To check out this is an Nijenhuis operator, it is a simple exercise. You can perform it at home using the formulas we have obtained in lecture 4. Right, you can take these formulas and see that, yes, of course, this is an Nijenhuis operator. Okay, this is an Nijenhuis operator. So we look at its characteristic polynomial, and we see that its characteristic polynomial is like this, right? It is x, y, so the coefficients of the characteristic polynomial are independent function. Important thing, we use minuses in the definition of the characteristic polynomial. Sometimes people use plus, but our minuses, they have a very nice explanation. The thing is that if you substitute operate into characteristic polynomial, you will get 0. It's a well-known fact from the linear algebra. In our case, our polynomial, it says that if you take the nth power of L, yes, it is expressed as a linear combination of smaller powers with a good coefficient. Because what we say, well, this is 0, we take all this negative part to the other side of the equation, equality sign, equal sign, and we just get this formula. So our notation has a nice meaning. It's not just we came up randomly with a negative sign here. So keep it in mind. But keep in mind that sometimes the notation, the usual notation, it might differ from the one we have here. So we'll take a look at this example. So we have this characteristic polynomial. And how do we explore the algebraic structure of the operator? Well, let's go back. We know, well, in dimension 2, it is rather simple, right? You know that in dimension 2, you have basically 3 cases. You have 2 real eigenvalues, you have 2 complex conjugate eigenvalues, and you have a Jordan block, right? The first case, it includes identity of 0, right? And the Jordan block, it means that it includes 0 Jordan block with a single eigenvalue. So what we need to do, we see, first we need to look at this operator. We see that this operator always has rank at least 1. It means that if I look at this operator minus something identity, it will always have rank 1. So nowhere, for no x and y's, the rank of this matrix drop below 1. So it's always 1, at least 1, maybe 2, right? But at least it is 1. So if it is at least 1, then basically we have 2 cases. We have pairwise distinct eigenvalues, real eigenvalues, because if you have 2 real eigenvalues that coincide, that the rank will drop by 2 if you subtract it, right? And we have the case of 2 complex eigenvalues, and if the eigenvalues coincide, then we have a Jordan block, right? So just looking at the rank of this matrix, we see, well, it's how this thing plays out. So it might be 2 complex eigenvalues, 2 real eigenvalues, pairwise different, and then if eigenvalues coincide, then this is a Jordan block. Okay, now how we just take a characteristic polynomial and calculate the discriminant like we do in school, right? So we want to know when these 2 eigenvalues are different, and we get the characteristic polynomial. It looks like this. This is a parable, right? You have a parable, and it splits the plane, as again, as I said before, this operator, it is Nijenhuis on the entire plane. So it splits in 2 parts, right? We have something we have above parable, and we see there that the eigenvalues, they're like this. See? This is a nice place to remember the following fact. If you have an operator, then its eigenvalues, they're, of course, they're continuous function, and we'll use it sometimes later in our proofs of some theorems, but they're not smooth everywhere. See? Because, well, it's an easy to understand the problem. It is easier to understand in dimension 2. Look at this formula. If I take any partial derivative, this square goes into the denominator, right, of the fraction. And there, if you have, if you get close, if you get to the point where this discriminant vanishes, right, you have a denominator which is 0, right? And this, thus, there is no, the derivative is not continuous, right? You have a rip here. And this is important thing. So we see that these eigenvalues, they're defined because this is an important thing, because in regular geometries, what we did, we took eigenvalues to be coordinates, or our eigenvalues were functions of the coordinates. Remember that, like in diagonal, it means that if I'll take this operator and bring it to the diagonal form, then each function will depend on its own coordinate. But here we see that these eigenvalues, they do not exist everywhere. So this operator, it is diagonalized above the parable here because we have these functions. But as we get to the close to the parable, the coordinate system, it breaks down. It's an important effect, which is important to understand why it's important to come up with a different form. Why do we study differential and non-degenerate? Because you can say, well, differential and non-degenerate, they like almost everywhere, because here it's 0 on some curve. Like almost everywhere you have different eigenvalues, then maybe you can come up with a coordinate system. And why do you need another coordinate system, right? Well, because those coordinate systems do not work. Now, on the parables, we have a L, which is Jordan block, and which is fun that in each point, those Jordan blocks are pairwise different because the eigenvalues, they become x over 2, right? And because x over 2, it parameterizes the entire parable. So in each point, you see that the eigenvalue is different. You have 0 Jordan 0 eigenvalue at the origin, and over these curves you have different eigenvalues. Okay. Below this parable, we have a pair of distinct complex conjugate eigenvalues. We know the normal form because below this parable we have a complex structure. We have one-dimensional complex space, and the operator, it has the form which corresponds to the single thing. It means it has. I think I should have written it here, but I hope you remember from the last time. So we see that the geometry is highly non-trivial. Look, you have a real eigenvalues, then get to the parable, then you have some Jordan blocks, and then you have transformation into the complex domain. So you see two different really different geometries glued together. You have like real geometry with a pairwise different eigenvalues, and you have a complex geometry with, again, two pairwise different eigenvalues. So this is actually the general case. So to understand that, this geometric thing, that those things we have observed in this example, they are generic. They appear in every dimension, because because here for the analysis we use the dimension 2 case, right? We said, well, look at the rank and stuff like that. So it is important to understand that we use the dimension too extensively. So we need to understand how it works in the higher dimensions. So we proceed like this. First, assume that P is algebraically generic and differentially non-degenerate for operator field L. It's not necessary in Nijenhuis, it's just operator field. And then what we know, right, because it's differentially non-degenerate, we have L, it has pairwise distinct eigenvalues, like those are first real ones, then you have a pair of conjugate complex ones, and the differential of these functions are linearly independent. Those functions are actually lambda and real and imaginary part of mu. We used this notation in previous lecture. This proposition says that it doesn't matter if your operator is Nijenhuis or not. What matters is that if its coefficients of characteristic polynomial are functionally independent, then the geometry in algebraically generic case is the same we have discussed, like exactly what we had before. We had like real above and complex below, and here it says because the dimension is higher, you have mixed geometries where you have some real eigenvalues, some complex. And of course, if you have a Nijenhuis operator, this proposition implies that you can bring it to the good form because you can split real part and complex part and do all kinds of things using splitting theorem. But in general, it turns out that this point-wise structure, it's absolutely the same. So I'm sorry, here it is. So what we do is we do the proof of the proposition for the real eigenvalues. It does not change for the complex eigenvalues, because those calculations, as you will see, they're purely algebraic. They do not use the holomorphicity of the functions to be holomorphic. We will see that in proofs of different theorems we heavily use this property, but here it is not. So what we do is, okay, we take this, we assume that all eigenvalues are real. We have a characteristic polynomial like this, because here we use this P is algebraically generic. It means that you have this number of eigenvalues and their multiplicities, they coincide. Okay, some of these eigenvalues, they can coincide. We do not know that. If they don't, we'll see that they don't. And then we write simply the vanishing of the characteristic polynomials. It means that if you what is a characteristic polynomial? To find eigenvalues, you solve a characteristic equation. You just equate the characteristic polynomial to 0. So it means that all the characteristic eigenvalues, they are the solution of characteristic polynomial. It means that it holds identically on the entire neighborhood, right? Because we have already established that we have eigenvalues. Okay, now then we take simply differential, right? If you differentiate each of these products, you will see that you get differential of this multiplied by this, and then this multiplied by differential of this. If you look at the differential of lambda in some power, you will see that, well, how does it work? You take a differential of this, n minus 1 goes here, and basically what you get is you get a characteristic polynomial, but not the characteristic polynomial, but its derivative. So what you get is you take characteristic polynomial with lambda I substitute to it and d lambda I. It's rather simple calculation. And all other terms, we gather them here, and we get the following formula. So we do this for different lambdas, and we get the following collection of formulas. Now, assume that lambda has multiplicity at least 2, then what does it mean that it has a multiplicity at least 2? It means that both the characteristic polynomial and its derivative, right, in independent variable, because characteristic polynomial is polynomial of a single variable, they do have a common root. And lambda I is a common root because you have a multiplicity 2, right? If you just look at this, if you have this power and you take a differential in t, and then you substitute lambda, you still get 0. So it vanishes. So we see that this part vanishes, right? And we get the identity. Look, we get an identity on the differentials of the coefficients of characteristic polynomial. It holds in every point, which means that these differentials, they cannot be linearly independent, because this identity, not all the coefficients vanish, because if lambda I is 0 at some point, then you have all the differential, they vanish except this one, which means that the differential of the last coefficient, which is determinant, vanishes, right? And it does not make it means that they are not linearly independent. If these lambda are not 0, then you get a non-trivial linear combination. So if this part vanishes, that this is identically vanishes, then we have a problem, and this means that all lambda i's must have a multiplicity 1. Now we take all these formulas for different lambdas and we calculate them and we put them all together, and we get the following formula, right? It's just symbolic writing, because, well, if you carefully look, this is not a vector or covector. This is actually a matrix with the rows being the differentials. Here is also a matrix with the rows being the differentials, but it doesn't matter. We symbolically write it like this, and we look at this matrix, right? What we know that this matrix has a maximal rank of n, and we want to know the rank of this matrix in a condition that each of these coefficient is not zero. We've already established that because this coefficient vanishes only if lambda has a multiplicity more than 1. This is a famous van der Monde matrix. If you did linear algebra, I'm sure you calculated the determinant of this matrix. It is basically the collection of pairwise the multiplication of lambda I minus lambda j, right, with some sign, I think, and it is usually proved by induction. But what is important is that because all these eigenvalues, the pairwise different, that this matrix is non-degenerate, and this matrix has a maximal rank, then this matrix also has a maximal rank. It means that all the differentials of all the lambdas, they're linearly independent. If you take complex eigenvalues into the mix, it goes absolutely the same, because, well, if you look at this, we did only regular algebra and linear algebra, and we didn't use any differential properties. And you will get that those differentials are linearly independent, and because the differential of complex valued function, because those eigenvalues, they're complex valued smooth functions, not holomorphic, but complex valued. It means that they are actually pair of functions, real and imaginary part. And if you take the differential is independent is if those real parts and complex parts, they're all independent and stuff like that. So it's quite simple. So that's what we did. We showed that in general point differential non-degenerate in general non-differential and non-degenerate point, you have a structure like this. It means that those eigenvalues, they are pairwise distinct, the differentials are independent. You can take them as coordinates if you have an Nijenhuis operator. And it says that our differential and non-degenerate geometry is a gluing of a very, very simple geometries, because we had different diagonal geometries, if you remember, when eigenvalues are not constant, but there are some powers. Remember that, right? No normal forms, we discussed that. But here we to take the simplest when all the powers are one, and we glue all the stuff together, and we'll see how it holds up. Because what we need to glue them, we need the singularities, because those regular chambers we've already described them. So we move to the singularities. Here it is. So now the next proposition, it implies that, well, the form we have met earlier in dimension 2, it is universal form of the Nijenhuis operator around differential non-degenerate point, right? So I wrote you that form. It looked really nice. And it turns out that around every differential non-degenerate point, which is important, it might be regular, it might be singular, we have these good coordinates, right? Okay, so we have this formula, and we need to prove it, like that Nijenhuis operator can be brought to this form. How do we do that? Well, it is rather simple. But we need to recall magic formula. It was written in terms of characteristic polynomial, if you remember. And but if you write it in terms of coefficients of the characteristic polynomial, it becomes in the form almost like this written here. Now, what we do, we take the coordinates to be the coefficients. Associated means that just x1 is the first coefficient, x2 is the second coefficient. And then we write the formula, and we'll see that in terms of these coordinates, the L star operator, it has the following form, right? And if we look carefully at this formula, which was called again, I think, magic formula in the first I think it was called magic formula in the first lecture, or maybe the second lecture, but somewhere in the beginning, and we see that this is exactly this form, because if we transpose this operator and apply it to the differentials or whatever, how you're more comfortably to work with, or use it or multiply it by rho, right? I like to transpose and multiply by column because it's more comfortable for me, but you can just take operator and multiply by row. It works, right? You will see that this is exactly the formula we have discussed. This formula is just rewriting this. So you basically apply this magic formula and you get exactly the proposition. So it's a simple proposition. So basically, we see that this normal form exists in around every differential and non-degenerate point, including of course, singular differential and non-degenerate point, which is important. In our example, parabola was a set of differential and non-degenerate singular points, right? We had their perturbation, and you see that actually, if you look at this form, you'll see that again at the coordinate origin you have a Jordan block with zeros, right? And you have the perturbation again, and you will see that the rank is preserved, but perturbation can be, as I said before, anything you like, with a limitation of the rank. Okay, so another important observation, this is a proposition, is that, well, singular points, imagine that we glued something together, like those geometries, right? And we have that geometric construction. And we ask ourselves how rigid it is. If we perturb it, will it like dissolve into some collection of different geometries? It is nice to have a strong, stable geometry, right? If you just perturb it a little bit in the category of Nijenhuis operators, of course. If you perturb it a little bit, it stays the same, right? It does not change. And this proposition, it says exactly this. So what is the perturbation? If we take a operator L, then we need a perturbation. The perturbation works like this. You have another operator, which is our Nijenhuis operator, plus some other different operator with a condition that at this P, because when we perturb, we usually perturb at the point, it has a zero of order K. What does it mean? It means that it vanishes, all the derivatives vanish, all the second derivatives, and so on and so forth, up to the kth derivatives, right? So they already may not vanish. Okay. So when we say that the singular points are C2 stable, it means that we perturb with the RK, which has a zero of order 2, right? It means that it vanishes, its first derivative vanishes, but its second derivative does not necessarily vanish. So we have a zero of order at least 2. It's a natural setting. It appears in all the dynamical systems. If you study integrable systems, it's a regular definition. This is like very simple proposition. You don't need even the proof because, well, you can see that it is obvious. Why? Because if we calculate the characteristic polynomial, if we calculate the coefficients of characteristic polynomials at point B, we will see that as functions in the neighborhood in the coordinates associated with L, right, they'll be linear functions plus some addition of higher order functions, because this is the what RK brings into the following, right? So we have we take the coordinates of L associated with functions, and we see that the trace is just first coordinate plus some higher order starting with the 2, for example, right? Then the second it's the x2 plus some higher order perturbation, right? And then it's just simply taking the differential. We take the differential and we see that differentials at the point they do not change by the perturbation of the high order. If they do not change, they're linearly independent because the perturbation is at least smooth. I'm sorry, that it at least continues because it's smooth. Then those differentials, they stay the same. They stay independent in the neighborhood of the point. It means the differentially independent, the differentially non-degenerate point stays differentially non-degenerate with a small perturbation. If it is so, then It means that we can apply the theorem we have proved earlier, not the theorem, I'm sorry, the proposition, which is again very simple. And we get that the geometry stays the same. So we see that this important thing that P can be singular point, right? We didn't use it algebraically generic. It means that these perturbations, they preserve them surrounding geometry, and it's really cool. It means that it's a good geometry. Simple, but good, because simple, you can see that it's simple, right? Because we all the statements we have proved so far, they're rather simple, easy, because it's not Thompson's theorem or theorem about complex structure or theorem about, I don't know, the eigenvalue of non-constant eigenvalue of the complex of the single Jordan block. Those like took a lot of space. And here everything is simple, but it's okay because it's like the simplest model we have. Okay, so we get very nice geometry. The singularities are C2 stable and not singularities, they are also stable. We have a unique coordinate system, but why it is unique? We didn't talk about that, I'm sorry. Because you take the coefficients of characteristic polynomial, and the coefficients, they are defined independently, invariantly. What you say operator field, you calculate the coefficients in each point, so you have functions in each point, and you have an order of these functions because they come in characteristic polynomial in the specific order, starting with the order of t n minus 1. So you have a single coordinate system. You cannot swap the coordinates because of the order, and you cannot change them because those functions are uniquely defined. So this is the unique coordinate system, which is again very, very cool because you have a nice coordinate system and it is unique. If you want to see some applications of this system, right? You just first of all you take a look at the objects you deal with in this system. We will see that later. It's really cool how this simple idea works and how this uniqueness. It's a really great thing for this exact geometry. Another thing is Nijenhuis operator is always GL regular. It means that we've discussed GL regularity in the case when we studied the constant normal forms. I think it was lecture 6. And there we discussed that what is GL regularity? It means that if you take the powers of L, they're linearly independent with identity. And this is the case, right? So we see that the rank is at least n minus 1, right? And if you take the powers of this operator, you will see that all the powers, they will be linearly independent. So this is just simple geometry and GL regular. Okay. And again, but in terms of if we have GL regular, we still perturbing, we can get different collections of eigenvalues in Jordan structures. But the GL regularity means that there is exactly one Jordan block corresponding to each eigenvalue. And we see that the eigenvalues, which are usually good coordinates, they are at most continuous functions. That is what we see is because we solve a polynomial equation. This is a general fact from the polynomial equations. If you have coefficients depending on some coordinates or some variables, if you solve it, you get at most continuous functions for the same reason we have discussed. Well, specifically, if you look at this, oh, I'm sorry, where this from? Here it is. See, here it is, because you see that the differential of lambda in point where you have non-coinciding eigenvalues, you take this and divide it by this, and you will see as we get closer to coinciding eigenvalues, that then the differential goes into infinity, and this is what happens, right? So it's still continuous, but its derivatives they break, right? So this is the regular thing from algebra, not from the geometry. So what manifolds can carry such a geometry? We do know that in applications, most of the applications, because, well, I'll be honest, our mathematical geometry, it's young, and there are a lot of questions we do not know answers to. And we do have some really good examples, a lot of actually really good examples, and we have a lot of really good applications, but there are still a lot of questions to be explored. So this question, we do not know actually the complete answer to this, like how do you classify them, or whatever, what can you say about this manifolds? Do they allow some classification or whatsoever? But what do we know is the next theorem. The next theorem, it's not about this geometry. It is a really, really good theorem about the complex part, because what we do here, the effect I have discussed is that, again, you're gluing different geometries together. Some of them are complex. In complex geometry is a very specific one. If you ever deal with the complex holomorphic functions, you know, right? Like the maximum principle and stuff like that. They are not your regular smooth or even real analytic functions. They differ a lot, and this is the case. So the next question, it's rather interesting, and this theorem, it answers the very specific questions which relates to the geometry we're discussing, but it's more general. I could have put this theorem earlier, but it wouldn't have been so interesting because we've already established that this geometry we're dealing with is interesting. And now we like step back and look on the problem as a whole, and we'll see that yes, the existence of complex eigenvalues, it's an important feature. It's a very important feature, and it puts some really strong constraints on the operator we can get. What are those constraints? I hope while I was talking, you've read the statement of the theorem. I hope you're not only listening, but watching. So in short, this theorem states that complex eigenvalues on a closed connected manifold, closed, it means compact, right? Without a boundary. It means like torus or sphere, something like that. On a closed connected manifold are constants. It's a really strong statement. It means that, for example, if we look if we go back to our geometry, to our two-dimensional case, right, then it is obvious that this two-dimensional case, those singularities cannot be realized on any complex manifold. Why? Because the complex eigenvalues here, they're not below the parabola. They're not constant. It means that if we have a small neighborhood in our geometry, and we think that it exists on some complex, on some manifold which is compact, we see that the problems appear straight ahead, because you have those complex eigenvalues, they are not constants, and they must be constant. So we see that this theorem puts a very strong condition that, well, it says the geometry is nice, it survives the perturbation, but it cannot exist on a compact manifold. It's okay. We didn't expect it to exist on a compact manifold. Well, actually, there are a lot of geometries with a hyperbolic geometry deals with a non-compact manifolds all the time. So we didn't expect them to be compact. So now we look to prove this theorem. It's not a simple theorem, because it's really a good theorem, because it requires different facts from different parts of mathematics, but we'll do that. Okay. So first we define the following function, right? We take the spectrum, which is collection of eigenvalues. We take collection of eigenvalues, then we take all the imaginary part and we pick a maximum of them, right? If all the elements of the spectrums are real, the imaginary part is 0, and it means that the maximum is 0. So the 0, the 0 set of this function is exactly the points where there are no complex eigenvalues. But as this function is continuous, right, then we have it achieves maximum and minimum. It is bounded, and we denote its maximum as mu 0. So if this is the maximum, and on a compact connected manifold, that's where we use compactness, achieves maximum and minimum. So we take this maximum to be mu0, and we say, well, let's not look at the entire manifold, right? Let's look at the specific manifold M0. What we're gonna do actually, very carefully, we're gonna pick the subset of the manifold. Well, the idea is simple, right? Okay, let me explain it beforehand. So if you have a complex function, right, what do we know? We have a maximum principle. What does it mean? It means if this function achieves maximum at a given point, and this maximum is in the entire neighborhood, then this function is constant. This is a very interesting property, and it's not the property of the complex functions only. It's actually a property of the functions that satisfy the Laplace equation. If you take a Laplace operator to the function equal to 0, then this maximum principle appears, right? And the Cauchy-Riemann equations, they do imply that both coefficients, both real and imaginary part of the holomorphic functions, they do satisfy the Laplace equation. And this is where the maximum principle in complex analysis appears. And we know this maximum. We want to use this maximum principle, but we cannot use it like straight ahead. Well, let's look at the eigenvalue. It is supposed to be, and so on and so forth. But well, actually, that is why we will need a couple of stages of preparation for us, because we want to have a good set. So we start with a set of M0. This is exactly the set where M mu function it achieves its maximum, right? It means that all the eigenvalues on this set, the real eigenvalues, all the non-real eigenvalues, they have a maximum coefficient, maximum imaginary part. So after we have constructed M0, we construct another function, which is Mx. It is a multiplicity functions, mult stay for multiplicity. What we do is we take this M0, right? And we go over the elements of the spectrum. If there are elements with imaginary part mu0, then we take the multiplicity of these eigenvalues. You can have several eigenvalues with the same complex, with same imaginary part, and those eigenvalues, they have different multiplicities. We pick the largest one, and if there is no eigenvalues, then you get 0, right? Because, well, there are no such lambda, which implies that multiplicity is 0. So M0 it's in functions which in each point of the manifold gives us a natural number, which is multiplicity. Let me say that M equals it is 0. This number is 0 if the function if the point is not in M0, and if it is in M0, then this function is at least 1. Okay. So we will limit this function on to M0, because what we know that M0 is a closed, and it is a closed subset of the compact manifold, and it is compact on its own. So we limit M to the M0, right? Because what we have just discussed, and we have a continuous function on a compact set, and it achieves its maximum and minimum. It is bounded again, and we will denote the largest multiplicity is M0 to be, right? And we say, well, let's take this largest multiplicity and fix another set, which is M0 tilde with a tilde. Okay, and we take this set, and this is exactly a set of the eigenvalues with the largest multiplicities, right? So what we have the entire manifold, imagine it like a sphere or something. What is easier for you to imagine, right? And what we say, well, we take first the set where the imaginary part achieves maximum, and then we take the subset where the eigenvalues with this imaginary part achieve the maximal multiplicity. Okay, right? So this is the set, and it is closed. This set is closed. How do we understand it? Well, first of all, the fact that set is closed, we understand it straight away. How? First, we look at the real parts of the eigenvalues, right? I'm sorry, this mu, it's supposed to be different name. This is typo. Okay, it's not the mu we have already used. It's different. So we say that we have this closed subset M0, and we have infinite. We take a series of points, infinite series of points belonging to the M0 tilde. This set of points is infinite, and what we know is that it's a complex imaginary part of the corresponding eigenvalues. They're the same. The multiplicity is the same, and because we take those eigenvalues with the highest multiplicity, but the real parts, they behave like poorly. They do not necessarily converge. So what we do, we take a subseries with a converging real parts. It is possible because the entire series is limited, because this function is continuous. It means that it is bounded. The real parts are bounded from above and from below, right? And this means that we can pick a converging series which converges to the same point, right? And those real parts, they do converge. Okay, right? So after that, we have a converging series of eigenvalues with the imaginary part is the same. Thus, the imaginary part of the limit is the same, but it was obvious because M tilde 0 is subset of M0, and M0 is closed. But which is important is that if you look at the multiplicity, then multiplicity is the same. Why? Because multiplicity of a given eigenvalue, it's basically the vanishing of some polynomial, right? Because we have already discussed it earlier. We say, well, when lambda is at least multiplicity 2, when it is a common root of f and its derivative. When it has multiplicity 3, when it's common root of f derivative and second derivative of f. And the common roots, they're calculated using the beautiful algebraic theory of resultants, right? It's a it's complicated. It's a calculationally heavy technique, but very, very interesting, very, very nice. Very, very good. I'm sorry. So what you do is you take those polynomials, you do the calculation, you get a polynomial with coefficients being the sum polynomials of the coefficients of the original polynomial, which is exactly the characteristic polynomial of L. And you get that this polynomial, it is defined on the entire manifold, and it vanishes in on all these points of our series. It means that it vanishes in the limit because it's a continuous function. Well, so we get that the multiplicity in the limit is at least M0, but M0 is the largest multiplicity, so it is M0, right? Again, we take a converging series, we take a subseries for the real parts to converge, we get that the limit has the same imaginary part, and the multiplicity is of the limit can be greater than M0, but it cannot, because M0 is the largest. So this is just simple, something from calculus, right? It's a calculus discussion. It's not a differential geometry, but again, it is important. We have established that M tilde 0 is closed set. Now what we're going to do, we're going to prove that it's an open set. That is, with a given point, it contains a sufficiently small neighborhood of this point. How do we do that? Well, we apply the theorem. What we do know from the previous one, if we take a point, right, and we look at the characteristic polynomial of this point, we will see that those eigenvalues with the highest multiplicity, right, they stay with the highest multiplicity in some neighborhood, and we get that our polynomial, it's actually split into the characteristic polynomial that corresponds to these complex eigenvalues. We have M0 multiplicity of complex eigenvalues, which means that M0 is the multiplicity of conjugate. Значит, it means that if we combine them together, we get a polynomial. We get polynomial of degree 2M0, right? Because you have M0 complex coordinates. It's again 2M0 real coordinates. We do get that this polynomial, so applying splitting theorem, we split into two parts. We just take this in this complex part, because the real part is multiplied. If we get what we want to prove, that something is constant, if it's constant on this part, it's constant on the entire neighborhood, right? Because that's how we construct the neighborhood. So we forget about the rest of coordinates, and we deal only with two M0 coordinates. We have a complex structure. We have already proved that. And what is more important, we have that those coefficients, and this we get that the operator with respect to this with this complex structure is holomorphic, which implies that the coefficients of the polynomials are holomorphic. And we split this. We split this characteristic polynomial into the product of two. One corresponds to the complex eigenvalues. The other corresponds to the conjugate eigenvalues. And we get that at the point P, we have that the first part, it looks like this, right? And we know that all the coefficients are holomorphic. Now, because we have those complex eigenvalues, they expressed in terms of our operator and stuff like that. So we define the following function, right? The imaginary part of A1. This as A1 is a holomorphic function, then F satisfies the Laplace equation, right? Here it is. We apply the Laplace operator and we get 0. And it satisfies the maximum principle. At the same time, we have that the value of the function at the point of this imaginary part, right? It is maximum. Why? Because, well, we know that the eigenvalues, they might change, which means that their imaginary parts might differ, right? And but the imaginary parts, they must stay the same. And but maybe the multiplicity drops and the multiplicity of other eigenvalue grows and stuff like that. But what we say here is, well, at most, this function equals to mu0 times m0, right? Because this is what we get, because this is at the origin. So thus we get its maximum principle, then it is constant. So we get its constant. Now we apply the Cauchy-Riemann condition to the holomorphic function A1, and we get that if the imaginary part is constant, then because of the Cauchy-Riemann equation, it means that the real part is also constant. And we get that A1 is a constant function of the neighborhood, right? So what we get, because A1 has a real nice meaning, we get that the sum of imaginary parts of eigenvalues is F, it is equals to M0 mu0. And at the same time, we have we know that the imaginary parts of some eigenvalues, they might drop and stuff like that. So because we assume that the neighborhood, we don't know how this neighborhood is, how it looks like. That is why we do not assume that we live still in M0 tilde, right? It's important. I should have said it earlier. So that is why when we say look at this inequalities, of course, for the points of which belong to M0 tilde, this inequality is not an inequality; it's equality, because all the imaginary parts are the same. But we know that because we assume that the neighborhood entire, it's not necessary in this set, then those eigenvalues, the multiplicity can drop, can grow, and stuff like that. What I said before. This was the motivation for that. So we look at this, and we see that. But the choice of M0 and mu0 implies that the imaginary part of each eigenvalues is not larger than mu0, right? And if the function equals to mu0, then all of them, they achieve maximum, right? So what we know is from the fact that A1 is a constant function, we immediately get that all the imaginary part of all the eigenvalues are also constants, because they cannot drop below this maximum, right? Because the function is maximum. Okay, we say, cool. But what do we do next? Locally, if you look at the operator, at the complex operator, you see that almost everywhere you can, as I discussed before, it was purely algebraic result. Almost everywhere, the eigenvalues of the of the characteristic polynomial or eigenvalues, which are roots of characteristic polynomials, they're almost everywhere good functions, right? We've discussed that they become bad functions where you get coinciding eigenvalues. But we say that, well, eigenvalues, they kind of may be different. And if they do not coincide, they do not coincide almost everywhere. So what we say is that, well, if we take it, the eigenvalues, they're almost everywhere on the neighborhood. They're holomorphic functions on their own, right? They are holomorphic functions on their own. But now what we get that if we take imaginary parts of all eigenvalues, they're constant, but the eigenvalues themselves, they satisfy the Cauchy-Riemann equation. We apply the same trick. See what we do here? We apply, basically, we apply the same trick all over and over again, like for this third time. We say, well, eigenvalues satisfy Cauchy-Riemann condition. If the imaginary part is constant, then the entire eigenvalue is also a constant. So that's it. Yes. Do you have a question? No? Okay. This implies automatically that all eigenvalues are constant. So again, what we did, we took a splitting theorem, we splitted the neighborhood, we carefully looked at the choice. See, that's what I started with. You need some work, some tricks. We've seen that first imaginary part of A1 equals to 0, then it is holomorphic, then it is imaginary part is constant, then you get the entire A1 is constant, then you get the entire eigenvalues, all the entire eigenvalues are constant. So that's it. And thus, by continuity, if they are constant everywhere, they're constant. If almost everywhere, they're constant everywhere, and we get that the entire neighborhood may be smaller than the one we started with, lies in M0 tilde, which implies that M0 tilde is also open. Then it contains the entire manifold. This is a topological fact, very simple, but it is. So what we do next, we take a new operator field, we kill off this constant eigenvalue, because what we have shown, right? We have shown that M0 tilde coincides with the entire neighborhood, with the entire manifold. It means that we have a single eigenvalue with a constant complex part. And I'm sorry. So what we need to do is we need to come up with a next operator with a different operator by this formula. So what is first, if we look at this formula first, we see that this the operator we get, right? It's a polynomial of the original operator with a constant eigenvalue, or with a constant coefficients, and this operator, it has thus, because it's with a polynomial with a constant coefficients, then its Nijenhuis torsion vanishes. It's a Nijenhuis operator, right? It's the first thing you can see from here. The second thing, well, you can see from here that this instead of mu, this constant eigenvalues, we prove that this constant eigenvalue, that this complex eigenvalue is constant throughout the entire manifold. It has 0, right? And 0 is a real eigenvalue. So if the original operator had several complex eigenvalues. We have proved that the one having the largest multiplicity is constant, and then we killed it off by multiplying like this. And we say, well, let's look at the operator which is different, and it has all the other different complex eigenvalues. And we apply this process we started earlier over and over again. We again define M0. It will be already different M0. We got define M0 tilde and stuff and so on and so forth. And what we get in the end, we get that eigenvalues, they all vanish, right? All the complex eigenvalues are constants. So we have proved the theorem. Now, if you have such a strong, like it's a very, very strong result, if you have such a strong result, you can apply it and use it to prove some interesting facts. We start with the corollary, right? First of all, it turns out that the observation we started with, right, it holds in arbitrary dimension. What does it mean? We have an operator field, right? We took dimension 2 and we looked at it and said, well, look, you have a complex part. So if you want to make this complex, if you want to take this singular non-degenerate point and realize it on some real manifold, then it is impossible. Why? Because if you do that, assume that it is possible for you to do that, then you cannot have constant eigenvalues. Same thing goes here, because if we look at the singular points for such operator, and we look at the polynomial, we'll see that the singular points, it implies that you have this switch between different eigenvalues. You see that those two eigenvalues, or more than two eigenvalues, they glue together and become complex valued. So basically, in every neighborhood of a singular non-degenerate point, you get a complex, non-constant complex eigenvalues, right? Because of the same calculations we have used earlier. So it is impossible. Another corollary is way more interesting. It deals with the so-called four-dimensional spheres, right? It shows it is an important proof of concept because, well, we say that this theorem is really nice, the one we proved it, but what restrictions, again, what restriction it puts on the Nijenhuis geometries of different manifolds? Because, well, actually, each manifold can be equipped with a Nijenhuis operator, right? It's a trivial Nijenhuis operator. You take identity operator and you multiply it by some function, arbitrary function, and you get an operator with a non-constant eigenvalues. They all coincide in every point and they're equal to f, right? And all those eigenvalues, they coincide, and you have this manifold, which is Nijenhuis. But it's trivial. There is not much geometry here, basically. Base function on the manifold, which is has nothing to do with what we want to study. So the natural question is, what the limits of like really nice limits you can come up with? And the following corollary, it really provides these restrictions. It goes like this: that every Nijenhuis operator has only real eigenvalues. It means that you cannot have complex eigenvalues. It means that, well, if there is a Nijenhuis operator, then it looks like this, right? It cannot have complex eigenvalues. How do we prove it? Well, the main result is a classical theorem by Girard. If you recall, we've already discussed it, that the almost complex structure is an operator field with identity that if you square the operator field, you get negative identity, right? So basically, the idea here is that the Stingray theorem it says that only two-dimensional and six-dimensional spheres have almost complex structure. Spheres of all other dimensions, including four-dimensional sphere, cannot have a complex structure, almost complex structure. Well, you have almost complex structures. The dimension is even, right? It's not odd. So if it's even, then you have like two-dimensional, four-dimensional, 6, 8, and so on. And it says this theorem that you have only these two spheres, and this sphere in dimension 2, it does have, beside almost complex structure, but the sphere of dimension 6, it's an open problem, very interesting one. If you have a complex structure on 6-dimensional sphere, the problem is that you have a lot of almost complex structures, and no one actually knows, are there any almost complex structure that satisfies the Nijenhuis condition, right? It is very complicated to check a Nijenhuis condition for the all possible structures, because there are a lot of them, you cannot enumerate them and stuff like that. So it's a very interesting problem. It is interesting also because you have from time to time the different papers appear, which in some people say, well, we have proved that there is a complex structure on 6-dimensional sphere, and the others say, well, we have proved that there is no complex structure, and people find mistakes in all of these papers. So we do not even have the conjecture, right? So it's a very, very nice open problem, because you do not know actually how it plays out. So we will use this fact, not the conjecture, but the fact that a four-dimensional sphere not only has no complex structure, but it has no almost complex structure. How do we proceed? We take an arbitrary point P and assume that it has only complex eigenvalues, 4 complex eigenvalues. The sphere is real manifold. That is why they come in pair of conjugate eigenvalues. So we take FL and we get a complex structure on S4. That's it. Okay, it's impossible. Well, because those eigenvalues become constant, right? If they do not coincide at the point, they not coincide everywhere. If they coincide, okay, they coincide, but we take FL and we get the complex structure. We have a complex structure because L is Nijenhuis and FL is also Nijenhuis, and it will, in square, it will be -1. So now we assume that it has 2 complex eigenvalues. We have a distribution of the kernel of this complex part. Then we take an arbitrary metric. We take the orthogonal distribution. So we have a 4-dimensional spheres with the 2 distributions, or each distribution is orthogonal to each other, and they all have dimension 2. Okay, because again, if you have 2 complex eigenvalues, applying theorem, they are constant, and you have really nice, because in general, as you remember, kernel is not a good coordinate, not a good distribution, right? But in our case, it has constant rank, so it's a good distribution. And then we define operator which takes the tangent vector decomposed into the direct sum with respect to d and d vertical, and you act it like this. L is regular L. It is this kernel is L invariant distribution, so it stays in L. And in orthogonal, it acts like this. We assume that it stays in orthogonal. Then we assume that its length coincide with does not change, right? So we have an operator like this, and we assume that the omega, which is a value form of the metric, that this thing is not less than 0. So we have basically what we say, we rotate this one plane, we rotate it in the positive direction onto the other plane, and the image of the original vector eta is the result of the action. So because of this rotation, we have this, and this is an almost complex structure, and we get that it is impossible. There is no such J's. So now we have a cyclic form of differentially non-degenerate Nijenhuis operator, right? That's what we're going to discuss. It's a very simple part. We go through it, I think, rather quickly. We start with a conservation law. What is a conservation law of operator field? It's a function. If you take differential, you take L star, and you take a differential again, you get 0. Sounds kind of complicated, but it has a very nice meaning. Consider a system of PDEs, partial differential equations. Those are quasi-linear systems. There are a lot of physical processes that are reduced to such systems. And we have that u is a vector function of two variables x and t. Lu depends only on u. It's not a linear system. If you take two solutions, you sum them up, you won't get the solution, right? So it's not linear. And Lu is a square matrix, usually written like this. And its component, they depend only on u. They do not depend on x and t, right? So they just depend on u. If we do the transformation, coordinate transformation, and we apply this, t stands for the derivative in t, x stands for derivative in x, then we will see that Lu is transformed as a linear operator. So if we consider u to be coordinates on some, let's say, ball or manifold, on some disk, then we get that Lu defines an operator field on this disk. So basically, we say that the system of quasi-linear PD is such a has a natural operator field associated to it. Now, what we say? Well, if F is a conservation law of L, by Poincare lemma, we know that this condition implies this condition. Locally, there exists function G. Then we can perform the following operation. Like imagine the integration of this part, because this function is function of x and 2. We get the function of t after integrating in x, and we differentiate it in t. We get t inside the integral, and we get the following formula, because what we take the partial derivative of f, and you will get a derivative of u in t. Then we take this, substitute this system here, and swap L onto the df, and we get, well, this is dg, and we apply dg, and we get the following formula. See, this is how we started, that's how we ended. Now, if we assume two things, first, this integral converges, it's some thing, right? It's not an infinity. Then, if we assume that this integral is 0, right? It is usually assumed in the systems like this that, for example, usually it has a physical meaning, like the solution, it decays on the infinity, So if we take a decaying solution on the infinity, then we get that the value of g in both plus infinity and minus infinity is the same. So this integral is 0 in some sense. If it is true, if it is 0, then this is a conservation law, right? It means that this integral is preserved with respect to this system. Differential in t does not affect it does not change in t, its integral. So that's where the name comes from. So the cyclic operator is an operator written in the following form. It's almost the one we had, only with the last row. And in addition, we put a condition like this. If we apply this operator L star to the differential of coordinate functions, we see that if we apply this to the first coordinate function, we get a second coordinate function, if second to the third. And finally, if we apply it to the last coordinate function, we get the following differential form, right? Because if we transpose it, then it will be in the last column. Then we apply dxn, and we get this. And if this condition is the closest of this form, right? In short, it means that we have a cyclic form if all the coordinates, they're conservation laws, right? This last condition ensures that we have exactly n conservation laws, because, well, if we do not use this condition, we get that first n-1 functions are conservation law, and the last maybe not, but we need n of them to get the cyclic condition. So we see that if we have a cyclic operator with this differential condition, this is a linear differential condition, then the following condition holds. We'll see that already this condition is not linear because we applied this to D and this omega, and we get L star squared, basically. So we recall that we have a, we already know that Nijenhuis operator can be expressed as a map from one forms to the two forms, and we apply it, and we get this short version because somewhere here there will be just the omega itself, which is a differential of omega, which is 0 because the differential of dxn is 0. This formula is again from I think from the lecture 2, and we get the following formula, and those two vanish because the vanishing of d omega is exactly the cyclic condition, and we get that the vanishing of Nijenhuis operator is the same as vanishing of this. Right, this star, it should be up here, up here. It's a typo. It's not some kind of weird multiplication. It's supposed to be like this. We'll see that this thing vanishes. Okay. And so we get that cyclic forms, because cyclic forms, they appear in application. And we see that in our Nijenhuis case, the cyclic forms, we have a very specific extra condition, right? That basically it says that you can continue this series of conservation laws. Now, we take non-degenerate Nijenhuis operator, and we get the following formula. This is just, and we define new functions, fk's, like this. And we can now try to express these functions in terms of coefficients of characteristic polynomial. Basically, this is a good algebraic problem from the absolutely different branch of mathematics. It has to do with the symmetric polynomials. If you take a polynomial with different variables, then polynomial is called symmetric if you interchange its variable in any way, and the value of polynomial does not change, right? And there is a natural, there's a very good theorem which states that you have a basis in symmetric polynomials. It means that you have a collection of basic symmetric polynomial, and you express any symmetric polynomial as a polynomial of these basic polynomials. So how do you do that? Well, there are some formulas which we will not discuss. They're called Newton-Girard formulas, and we just write three of them. They look like this. So we say that in these new coordinates, in these coordinates where we take these new coordinates, our differentially non-degenerate operator is in cyclic form, in this exactly form. But those in our regular form, we had this column. They were like the functions that were in this first column, they were linear, right? And here we do not have linear functions. We have polynomials, but we have the last column. So we see that our differentially non-degenerate geometry, it includes a good form of cyclic geometry, right? You need only to change the coordinates to the different thing. And to end this function, we discuss the last topic. We were supposed to discuss it, I think, earlier, but I had to move it because we had a large theorem to prove. And this is the symmetries of the Jordan block. You recall that the symmetries of the constant diagonal Nijenhuis operator with constant eigenvalues, semi-simple, we have that they are governed by n functions of single variable, n functions of single variable. So what we do want to know here, we want to look at the coordinate changes that preserve this, because there, what was the symmetries? You take a coordinate change and you simply calculate that if you take the coordinate change, then each of the coordinate depends on its own coefficient, then the normal form of the Nijenhuis operator preserves. Same thing here. We want to ensure the preservation of this Jordan block. How do we do that? We recall that under the coordinate, what we do if we went to preservation, that means that this and this, they are equal because this constant form, you do not need to substitute anything. Then you multiply it by this, and you get the following formula. So we say that we're interested in the following coordinate change, which has a very specific Jordan matrix, which commutes with this operator. If you go and do the calculations straight ahead, it's a good exercise. From linear algebra, you will see that the only matrices that commute with L, it's a very strong algebraic condition, are the matrices of this form. See, you have something on the diagonal, then something above the diagonal. On all these numbers, they all coincide. So this A1, they all coincide, A2, they all coincide, and so on and so forth. This implies that Jacobian matrix is in this form, and we have we get that if we remember what is the entries of the Jacobian matrix, we'll see that, well, the last function, it must, because all of them are this, all of these derivatives are zero, that means that depends on xn. Then we get that the one before last, it depends on the last coordinate and the one before last, and all is zero. Moreover, it depends very specifically because those two coincide. It depends on xn. It also depends on xn. So if we look at these two things, we'll see that, well, it's supposed to depend on xn minus 1 linearly, because if you take the derivative, you get the function which does not depend on xn minus 1. So it goes like this, and we see that this the Jacobi condition holds if and only if you take this condition, that the change in last coordinate, it should be non-degenerate in terms of dependence on xn. You should recall that in case of diagonal Nijenhuis operator, we had a coordinate change which is supposed to be non-degenerate in all the coordinates, right? So we had a change in first variable, it's supposed to be non-degenerate. In second variable, it was supposed to be non-degenerate and stuff. And here we see that the degeneracy is important in one basically part, right? Because of this algebraic form. So it turns out that there is a natural and good way to describe all the symmetries and to describe them algebraically. It is some sort of implicit integration procedure. What does it mean? It means that, well, basically, if we look at this system, we'll see that we need to solve a system of partial differential equations because, well, we have a system of partial differential equations. So we say, well, this system can be solved. We can write a algebraic procedure that generates the solution. Later we will see that these are all solutions, but for now we just show that these are solutions. It means that we can show that we can generate sufficiently large collection of functions. So what do that? How do we do that? We take M and write it like this. See, L is this function, right? And we get that basically we get M. Here it's xn minus 1, and here instead of an it is x1. So we get this function, and then we take n arbitrary functions with only one condition, that the last function, its derivative at 0 is not 0. And okay, we work in an analytical category. It's important. So we write the following formula. See what we did here? We substituted m into the function. Because these functions are analytic, we get the large analytic formulas. And again, instead of analytic functions, we could have used Margolins functions, which satisfies Margolin's condition, which is also an important thing. But here we restrict ourselves to analytic functions. So, and we'll see that by definition, this formula yields the following. We have this this GM, it commutes with L. It means that it has the following form. It means that if we do all the calculation, we get the matrix which depends on coordinates x, but in very specific form. You have n functions. See, you have a function here, function here, function here. If we, let's say, we take fn equals just 2x simply, and all the other functions are zeros, we get exactly the formula for m, right? But if they are not zeros, we get some more complicated stuff. So we have the proposition that though the coordinate change using this function gi's, it actually is a symmetry. It preserves. So how do we prove it? First, we calculate the derivative of gm. It goes like this. See, we calculate m in x, and it gives us this because that's how we defined m. And here we have a derivative of the following form. L does not depend on x. And we see the following identity. See, so we have different derivatives of GM. They are related by the following matrix identities. This is matrix, and this is matrix. See, here it is. Okay, now we see that this identity can be written in the following form, right? Instead of 1, you can write J. And then you get, after you take G and you substitute this formula in terms of G's, in these G's, right? You get the following formula, see? You take the derivation of G and you apply L and you get the tail. You see that Ln minus 1 Lj for J larger than, for any J, it yields, I'm sorry, it yields 0. And that is why we get this tail. And because of this condition, because from one hand, this is this formula, and from other hand, applying this condition, we get this formula, we have a relation between the derivatives of G. And these are relations as follows. These are exactly the relations we wanted. We see that these G's, they're related as we wanted. The Jacobi condition is diagonal in the form we needed. Thus, this is the symmetry. Here is an example. Let's take a function to be t plus t squared, and all others take 0. We take gm. It looks like this. It's m plus m squared. Then we calculate the functions g. They look like this. They have linear parts plus something, linear part plus something, linear part plus something. And the coordinate change, it goes like this. These functions yield us new coordinates. This is a very nice procedure. It shows that you can integrate the stuff. And later we will discuss that these functions are exactly all the symmetries. So this description of the symmetries in an analytic case is a complete description, which is again a very interesting fact. Okay, any questions? Well, okay, thank you very much. See you next lecture.